in a straight line along a rough horizontal surface. Obviously, if the surface is rough, then it means that there will be frictional force, and remember, frictional force always acts in the opposite direction by a varying force x. So we are saying this force x here, it's a varying force, it's not a constant force. It will change that force x. Air resistance is negligible, so we don't have actual air resistance, only a frictional force between the ground and the block. Assume that the frictional force exerted on the block by the surface is constant. So, and there's a magnitude of 2. So our frictional force, we are told it's constant. Obviously, it will be going in the opposite direction here. And also, it has a constant magnitude of 2. It's safe to write it like that. So the variation with time t of the momentum p of the body of the block is shown. So we actually shown the graph of momentum against time. How momentum is changing with time. Okay, fine. So then we go further. Use figure 3.2 to determine for the block at time t is equal to 2 seconds the magnitude of the resultant force on the block. So imagine this. We have a graph here. Okay, before I do that one, let me do the first part. Question A. Question A said state Newton's second law. I had already written this for you so that we don't waste time on this one. Obviously, Newton's second law is the rate of change of momentum is directly proportional to the resultant force. Sometimes we actually say that the rate of change of momentum is equal to the resultant force. So that's why sometimes you see that we can write it like this. We say the resultant force is equal to change in momentum over time. Change in momentum over time being the rate of change of momentum. F being the resultant force. So resultant force is equal to the rate of change of momentum. That's Newton's second law there. So then we go for the question B. Use fig 3.2 to determine for the block at time t is equal to 2 seconds the magnitude of the resultant force on the block. So we want to know the magnitude of the resultant force on the block. So remember, if at time t is equal to 2 seconds, we can go on this graph and start when time is 2 seconds. Okay, so we are being asked at this particular time to find what the magnitude of the resultant force. So how would we find the magnitude of the resultant force in this case? We need to be very careful on our understanding of physics. This is a graph of momentum and against time, and as you can see, momentum is increasing at a constant rate here. The graph is a straight line graph, and momentum is increasing at a constant rate as time changes. You are being asked to find the resultant force. So obviously, suppose we were to find the gradient of this graph, don't you think that the gradient of this graph will be delta p over delta t? And what is that? Isn't that change of momentum over time, change of time? Isn't this equal to the Newton's second law, which gives us the resultant force? Because that's the gradient of the graph. So the gradient of this graph of momentum against time actually gives us the resultant force, because this gradient of this graph is giving us change of momentum over change of time, which is actually equal to the resultant force. So first things first, this is something that we must understand. So having understood this one, then it means that if we want to find the resultant force at this particular point, which you want to find the resultant force, we must actually find the gradient of this graph at that particular point. But the gradient of this graph at this particular point is a constant starting from this point 0 to this point, this one. So instead of just finding the gradient at that point, we can find the gradient at any point starting from here to here. It's the same thing. It's a straight line, so the gradient is a constant. So finding the gradient of the entire line is the same as finding the gradient at that particular point where we want to find the gradient. Okay, so now these are my coordinates to find the gradient: 0 and 0. Then here 6 and 4. There is no worry because the units here are fine and the units here are fine, so there's no need for conversion, and everything is in the proper units. So using those, I could say that firstly, my resultant force is equal to the final momentum. Final momentum, as you can see from the graph, is 6 minus initial momentum, which is 0, over change in time that has happened during that interval, which would be 6 over 4, which gives us 1.5. So our resultant force is 1.5. Then next, the question asks us to find force X. Now, you must always understand that if a body, we are looking for force X at this particular instant at a time t is equal to 2 seconds, where there is a resultant force, where there. So we need to, if we are going to find a force X, we need to know all the forces acting on the body. Now remember, on this body there is no air resistance. So if there's no air resistance, what are the forces acting on this body? Then there's force X. Then there is the resultant force. There's the, what is it? The frictional force, which we are told that is 2 newtons. Besides that, we are told that there's a resultant force. So I would put an arrow there to show the resultant force, which we have just found to be 1.5. So we have a resultant force. These are the forces acting on the body. So we cannot find force X unless we know the forces acting on the body. And the force acting on the body is the resultant force of 1.5, which is the result of this force X and the 2 Newton force. So now, understanding this now, we will say, okay, so how would you look for the resultant force in this question? You would actually say force X minus the 2 Newton force. This is what gave you the resultant force of 1.5. So ultimately, force X is equals to 2 plus 1.5 newtons, which gives us 3.5 newtons. So the force X is 3.5 newtons. Okay, we have simply used basic logic really. Next now says, on figure 3.3, sketch a graph to show the variation of force X with the time t from time is equal to 0 to time is equal to 6 seconds. Now it is apparent here, if you check out carefully, that since from this point here to this point the graph was a straight line, then as we have told you, then that means that the resultant force is a constant during that region. Number one, we have already been told that the frictional force is a constant, meaning that if frictional force is constant and resultant force is constant, then that means that the force X will also be constant. So the force X will be constant at 3.5 as we have found it. Now, what about this region from here to here, from 4 seconds to 6 seconds? From 4 seconds to 6 seconds, the gradient is 0 here. So if the gradient is 0, it means that the resultant force will be 0, because the resultant force is being given by the gradient of the graph of momentum against time. So if the resultant force is 0 from the final part of the graph, then what can we say now? Because remember we had said that actually the force X is equals to the 2 Newton force plus the resultant force at that particular time to find for that region there. And we found 3.5. But what if now in this region now the resultant force is 0? So it will be 2 plus 0, which will give us 2 newtons. So for the remaining 2 seconds, from 4 seconds to 6 seconds, the force X will be 2 newtons. So we are so clear of what we want to do here. So we're going to come here and we'll draw a graph showing the regions. So firstly, we have a straight line here to this point, then we go down, then we have another straight line here. Okay, let me revisit that one. Okay, so that there is our graph. It is representing that from 4 seconds to 6 seconds here, the resultant force is 2 newtons. The force X is 2 newtons. And from 0 to 4, the force X is 3.5 newtons. That is it. Okay?